So today's lecture is going to be on encoders. Has anybody worked on encoders before, or does anyone know what encoder is? So what encoders are, these are going to be in the digital system. Okay, so if you happen to work in a digital system, you can't spend a day working, not having your hands on encoders. So the encoders are basically combinational circuits, and they actually fall under small scale integration. Remember lecture number 5, we had one slide where we were looking at the classification of different integrated chips. So small scale integration would have, actually medium scale integration, and they would have around 30 to 300 chips, 300 gates per chip. So encoders are basically used to encode the data, transforming data from one format to another. So say you have data in hexadecimal, you can convert it into binary. So I want to actually throw one example right here, which I should be doing at the last, but I just want to throw at the beginning of this lecture so you really understand what encoders are. So actually, if you look at it, this is a positional encoder. It's used for navigation applications, so like for ships and cruises. So if you look at this, this is actually a compass, and it has 8 positions, north, northeast, east, southeast, and if you look at the needle, the position of the needle in this compass is actually pointing towards the east. And so therefore, if you see the logic, it's actually 1, whereas it's 0 for the other data lines. So notice if there are 8 data lines, D0 to D7, each of these data line is connected to the position in the compass. These positions are going to be triggered using the reed switches or some kind of sensors or magnets that you would arrange in the compass. And because the needle is actually pointing towards the east direction, so D2, the data going into data line 2, is actually 1, and it's 0 for the rest of the other combinations. And what it would generate at the output is actually going to be the binary code of that line for which the output is high. So if you notice, D2 is high, and the binary code for D2 is 10, so it generates 0, 1, 0. Now, what is the relationship between the inputs and outputs in an encoder? So the relationship is actually given by the equation where you have n equals to the power n. Okay, so this is going to be your inputs right here, and this is going to be your output. Okay, so if I put these numbers in this equation, I have 8 inputs, so I got 8 equals to the power, so number of output has to be 3, right? Because this is how it makes sense. To the power 3 is equals to 8, so we have 3 inputs which are going to be right here, and we have 8 inputs going in. This is also useful in a way that you basically have an 8-bit data, but you have encoded it into 3-bit data, basically having 8 wires to 3 wires, so you are shrinking the size of your digital system or device, whatever you're working on. It's easy to deal with 3 wires versus 8. So this is what encoders does. We're going to do a bunch of examples and also different kind of encoders that are available. So I just want to quickly go through some of the lecture notes which are also available on Canvas. So these are combinational circuits. They fall under medium scale input, like I was mentioning earlier. Encoders have n input and m outputs. The relationship between the inputs is such that you have this equation. This is going to be your inputs on the left, and this exponential power is going to be your output. The encoders encode data. Digital encoders take all of their data inputs one at a time. So if you notice the example that we just did, it was taking one data at one time. Discuss one more thing here on this example. So we are taking actually 8 bits here, which each bit is actually connected to one magnetic position. And you would feel that it might not be the most accurate way of getting a position data from this. So how can I increase that? Say I wanna know if there's any degree change in the needle. I want to know that. So how can I do that? So if I have more sensors in there, more magnetic components in there, say for 1 degree change, and because the circumference of the circle is 360, so if I need to have 360 of those, and that would give me a change by 1 degree needle of the compass, right? And therefore the configuration of the encoder would change. Then 8 by 3 would not work. We would need 360 by something. Okay, so we need to go for a bigger size of the encoder. All right, so coming back to this right here. So encoder encodes take all of their data inputs one at a time and converts them into an equivalent binary code at its output. They are also known as binary encoders. They can also encode decimal, hexadecimal to binary. So here's a block diagram of a 4 by 2 encoder. You got 4 data lines, D0, D1, D2, D3, and you got 2 outputs, Q0 and Q1. So for every case, there will be a single input, D0 and D1 will be high, or D2 or D3, which will be high. For example, if D1 is high, the output will be what? Because D1 is high and the binary code for 2-bit binary code for 1 is 0, 1, so it's going to generate 0, 1 at the output. So it's pretty simple. So if it's D3 is high, the rest of the other are low, it's going to generate 1, 1 because the 2-bit binary code for 3 is 1, 1. Okay. So this would meaning instead of having 4 data lines for output, we now have 2 data lines. So we are compressing the data, saving space and data lines. At the receiver end, this data Q0 and Q1 can be decoded using the decoder to get the actual data. We are not going to learn about decoder, but decoder is actually opposite of the encoder. So we can actually take the output of the encoder, feed it into the decoder, and then we get the original data what was here. Okay. So this is the relationship between an 8 by 3 encoder. This was also in one of the examples right here. Encoder is a very convenient way of using Boolean expression if the minterms are given without having to use the logic gates. And I'll show you, we'll do a couple of examples of that. Types of encoders, we'll start with priority encoders. Okay, so let's move on to the supporting material now. Okay, so I got a little bit more theory here. It's a device also known as a transducer, a software program or algorithm, or person that converts information from one format or code to another. The purpose is standardization, speed, secrecy, security, or saving space by shrinking size. And again, you have this encoder here that encodes the data. It goes into the processing unit. It makes a decision based on the information that it gets, decodes it, and then transfer it to the analog. So this information is actually exactly what it is over here. Okay. Moving on to the types of encoder, the first one we're going to learn about is the priority encoders. Design a 4-line, 2-line priority encoder with active high inputs and outputs. What does active high input means? When we are talking about the ICs or chips and we say active high, that basically just means 1 is on and 0 is off. Okay. In other words, 5 volt is considered as logic level high, 0 volt is considered logic level 0, and you would mean 0 is off. So this priority encoder 4 by 2 is actually connected to enable right here. So this could be your VCC. Usually it goes through some resistance right here connected to VCC. So because it's connected to VCC, that means it's enable, or in other words, we also use term active. Okay. But if we have this enable connected to ground, say, so that would mean this is disable. Or inactive. Okay. Problem with the encoder is we just saw that at one time it takes one input which is high. What is going to happen when we have more than one input that are high? Then it might be very confusing for the encoder, and that is where priority encoder comes in very handy for us. Note that the output of the encoder is the binary representation of the input. Within the priority encoder, we assume that all inputs will not be 0 at the same time. It's not possible that we have all the inputs 0. So say we have 4 inputs, D3, D2, D1, and D0. And we are going to complete the truth table for it. And so these are the inputs right here. And Q0 and Q1 are the outputs. You can label them over here also, D0, D1, D2, D3, and then you have Q0 and Q1. Okay, and we want to set the priority such so D3 has the highest priority here, and then D2, and then D1 and D0. What it means, if D0 and D3 are both high at the same time, what should be the output here? If this is 1, and this is 0, this is 0, and this is 1. Now we have a situation where we have more than one inputs, both set to high, and because D3 has a higher priority than D0, what should be the output over here? It would be 1, 1, right? Because that's the binary code of 3, correct? And because D3 has a higher priority, so that's how it's going to generate 1, 1. Now, keeping that in mind, we are going to complete this truth table. When we have D3, D2, D1, and D0 all set to 0, what would be Q0, Q1? Remember, we assume that all the inputs will not be 0 at the same time. An encoder, for it to work, it has to have one input line set to high. So this is what we consider as a don't care condition. Okay, here. Just forget about valid signal for now. So this makes a code of 0. We're going to move on to 0, 0, 0, 1. What should be the output now? Yes. So notice it's D0 which is high, and the 2-bit binary code of 0 is 0, 0, right? Okay, so this is 1. Here I have 0, 0, and D1 is 1. Can I write D0 as don't care here? If I can, then why? Yes. Correct. So because D1 is a higher priority, I really don't care whether D0 is 0 or 1. So this is actually covering 0, 0, 1, 0 and 0, 0, 1, 1. So it's actually covering 2 to 3. And the output will be what here, guys? 0, 1. Thank you. If I have 0, 1, and then again I can have these as don't care, what would be the output here? Yes, correct. You don't necessarily have to raise hand, just say, that's okay. As long as all of you don't say it at the same time. Actually, I don't mind that. Yeah. Okay, so this would make a code of 4, 5, 6, and 7, correct? Right? 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1, correct? Okay. And then we have 1 here, and then this will be don't care. Okay. So this will cover the decimal numbers in the range from 8 to 15, correct? And the output will be what here, guys? 1, 1, okay? This was really not needed, adding one more output, which is valid signal. But this just, I just wanted to add like, hey, I want to know whether the signal is valid or not. So notice for this combination, it is not valid, so it's 0. Because you cannot have all the data lines set to 0, and the rest of the other combinations is going to be 1 because at least one of the input is high. Okay, is everybody following me? Okay, so next up is the K-map. Okay, so 0 is don't care. We're going to do it for Q0 and Q1. This is 0. So we are looking at Q0 here. Okay. 1 is 0, 2, 3, 0, 4 to 7 are 1. 8 to 15 are also 1. So all of these are going to be 1. And I can actually make a set of 8 here. And also I can make another set of 8 right here because that would give me the most minimized expression right here. So my expression for the blue rectangle would be, the common is, so again we have D3, D2 here, and we have D1 and D0 here. So the common here is D3 plus, and then if you look at this green rectangle right here, the common is 1, which is D2. Now we're going to do the K-map for Q1. So we look at this column right here, Q1. 0 is don't care. 1 is 0. 2 and 3 are 1. 2 and 3 are 1. 4, 5, 6, 7 are 0. 8 to 15 are 1. So 1, 1, 1. 1 here. Again, I'll make this set of 8 here. What else I could do here, guys? Correct. So we will make a chord here. So now expression would be, for this green it would be D3 plus, and for this chord, so the common here is 0, so D2 bar, and the common here is D1, D2 bar dot D1. Okay, now we're going to take those expressions and we are going to create a logic diagram. Okay, you just need to connect the wires. I already have the gates in there, so let's work on D2 bar dot D1. So this is my D0, D1, D2, and D3. Okay, and then D1 goes in here, and the D3 goes through this OR gate, so I can just connect this here. So this would be my Q1. Okay. For Q0, I got D3 plus D2. So okay, so this was D3 and this is going to be D2. Okay, so this makes my Q0. And then I actually went ahead and did the K-map for valid signal, and I came up with this expression right here, D0, D1, D2, and D3. So I'll just write down here D0, D1, D2, and D3. And this is connected to this V valid signal right here. We also would like to verify this block diagram right here. So say I have all ones, say D1, D2, and D3 1. So because all of them are set to 1, and we know which data line has the highest priority here, D3 here, correct? So at the output we would expect we should get double 1, right? 1 1. So this goes 0 here, and this is 1 here, so you get 0 here. Okay, 0, and then D3 is 1, so you get 1 here. 0 and 1 going through an OR gate, you get 1, correct? Okay, D1 and D3 both are 1 high, so you get 1 here, and that's what we were expecting. D0, D1, D2, D3 both were set to high. D3 has the highest priority, so you get 1 1. That's the binary code for 3. and this is going to be actually one of the inputs is high, the output is going to be high, so it's a valid signal. And this was my end. So what is inside a 4x2 priority encoder? This is what you have. Okay, all right. We will actually do the coding for it also. So I went ahead and put some labels, some comment there also for you guys, so it's a lot more easier for you then. So we actually gonna have to come up with a module name. So say module space, say this is a 4 to 2 encoder. D input Q or, and let's say V here. Okay, we define our inputs, so I'll just do it as an array. So we have 4 of those D, comma, we have yeah, that's all we have. Okay, so these are basically D0, D1, D2 and D3. At the output we have Q, and we have Q0, Q1, so 1, 0, Q, comma, and then we have valid signal V. Okay, we're gonna go with the data flow modeling because the structural modeling may be too much here. Like here we're gonna say assign Q1 is going, and the expression for Q1 is right here. Okay, so this will be D3, or this is invert of D2 ending with D1, semicolon, assign Q0. So Q0 is, expression is right here. D3 ORing with D2, and then we can have last of the output, which is the valid signal, assign V equals to, and here's the expression for valid signal. So it's basically all the data lines ORing. Yeah. One thing that you remember, that you should always have this square brackets here, okay, on the numbers 2, because you have declared them as an array over here. So similarly, you will have D square brackets and 3 in there, okay, and similarly over here, D0 ORing with D1, ORing with D2, ORing with D3, and then in the end you say end module. Okay, and semicolon, not to forget that. One of the things that you would learn using the Vivado is how to troubleshoot. And if you're missing a semicolon, you might have experienced that in the last lab yesterday. It's very sensitive language, and it's very picky about small things. Okay, so it's a good learning experience. When you get an error, don't get disheartened. Actually, think of it as an opportunity to learn how to troubleshoot things. Okay, does the code looks okay? Okay. Okay. Also, one thing that I usually practice, which I didn't do it over here, I would not start the module name with a numeric value. I would just say 4. Okay, 4 to 2. Write in text instead of a numeric. Here, semicolon here. So it looks like the code looks okay now. We got all the semicolons on each line. We got our arrays all right. We have assigned all our outputs, and then we got all our inputs. Another thing that you could do here, if you like, you can also put a data type here, okay, which is a register. And we know, I told you guys what register does, right? Register is going to just store your value there. So once Q0 and Q1 both are 1, they will stay on. Even if I don't add register, they will still stay 1 here. But any change to the inputs, they will change. So you want to store them. So start just practicing now, because once we move on to the sequential circuits, this thing will be very necessary. It's not really necessary in the combinational circuits, and these are combinational circuits. So even if you don't add it, it won't have an effect upon the functionality. Once we start doing sequential circuits, you're going to have to declare these as registers. Okay, so it's good that you start making habit of it from here. Okay, everybody following me here? Okay, let's move on to our second type of encoder, which is a decimal to binary encoder. Again, these we got our inputs here, 0 to 9. These are our outputs right here. And basically, you're just making a binary code here. So for the binary code for 0 is 0, 0, 0. For 1, it's 0, 0, 1. For 2, it's going to be 0, 0, 1, 0. 0, 0, 1, 1. 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. Okay, so this is your input I0. This is your I1, I2, I3, I4, I5, I6, I7, I8, I9. These are my outputs here. So D3, this is my most significant bit. I got D2 here, D1 here, and D0 here. This is my least significant bit. Okay, so say I have 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. What should be at the output here? Yes. Which one will be on? D2. How did you come up with that? But I didn't mention what the priority is yet, right? So you can't really answer this question unless you know the priority. So I'll just go the other way. If I set the priority like this, okay? Okay, so from bottom to top, that's your priority. So what should be the output here now? Which data line has the highest priority here? Come on, guys. It's I0, right? I0 has the highest priority. What is the decimal code for 0? So it's all going to be 0. Okay? All right. You can make a decimal to BCD encoder. It actually just became decimal to BCD priority encoder. Okay. You can add priority to any kind of encoder. What are these min terms? D0. If you look at D0, just look at this column right here. So we have those are 1, 3, 5, 7, and 9. Yeah. So 1, 3, 5, 7, and 9. Let's look at D3. D3. So D8 and D9. 8 and 9. Okay. You can finish this later. If you look at the logic diagram below here, so which one of this is D3, if I ask you? The top one is D3 or not? So I was looking at the min terms here, right? These are all min terms, correct? And what do we do with the min terms? We add them together, correct? So we have OR gate, which are adding all those terms. And if you look at what is going in here, you got line number 8 and line number 9 going into this OR gate. So this would make what? D3, correct? So this is your most significant bit. Okay. Similarly, this will be your D2, your D1, and your D0. Okay, so if you look at D naught, we had 1, 3, 5, 7, and 9 going in here. So you got 1, 3, 5, 7, and 9 going in here. So that is your least significant bit. Okay, it's pretty simple. Before we move on to the third type of encoder, here's a opportunity for us to learn about active low inputs and outputs, which you will be doing in the next lab actually. So notice we have 4 LED segments on our basis 3 board. Those, all of them are active low logic. Means in order to turn them on, you need to provide 0, not 1. Okay. Right. So here's just an example, just to make you feel accustomed with the active low. Some encoders are active low, some encoders are active high, some decoders are active low, some decoders are active high. That's why it's very important for us what's the difference between the two. So in this example, it's a 10-line to 4-line encoder, and then the active low inputs and outputs are also active low. Okay. So if you look at so these are our data lines. We got so this, if I have this arrow and if I have this slash right here, it means it's an array and it's got bits from 0 to 9. So basically 10 lines. And I have the outputs right here, which are D3, D2, D1, and D0. If you look at the values for each data line, it's 1, 1, 1, 1, except for 9, which is 0. So active low, which would mean which of the data line is active here? Say it again. 9, right? Because it's set to 0. So, and we know the output of the decoder is such, you actually create a binary code for that line, right? So what would be the output here? We know that the binary code for 9 is 1001, correct? But because this device is active low, so we're just going to invert the bit. So it will be 0, 1, 1, 0. Correct? Okay. Meanings D3 will be high and D0 will be high. Okay. So it's just the opposite of it. So don't get confused. Say we move on to here, this line right here. So we got 6, data line number 6 is 0. Rest of all of them are high. What is going to be the output here? The 4-bit code for 6 is 0, 1, 1, 0. So the output will be? Come on, guys. Correct. Awesome. What about here? Notice we got 2 zeros here, 4 and 7. What would be the output? Okay, say the priority is this way. What would be the code now? 1011. Okay, so 0100. So he said 1011, which is actually correct. Good, awesome. Also, some books would have like H for high, which is basically 1, and L for lows. So also, if you're reading, say, reading from Zahid, he actually prefers to use H as in high for ones and low. So also we'll practice one for that. Here, what is going to be the output in terms of H and L's? So 5 is low, the rest of the others are high. What would be the code here? Tell me in H and L's. Okay. We know that the code, the 4-bit code for 5 is what? 0101, right? We are going to invert this, right? So it will come down as 1. I'm just writing it in a subscript. 1010. Okay. 1 is high, 0 is low. 1 is high, 0 is low. So it will be HL, HL. Okay. All right. What about this right here? We got 7, 8, and 9. Both are set to low, and the priority is actually increases moving from right to left. What would be the output here? H, L, L, L. Correct. 7 makes a code of 0, 1, 1. So inverted, you get 1, 0, 0. 1 is high, and 000 would be 3 lows. Okay, so that was just a. We'll actually go to this third type of encoder, which is octal to binary encoder, and I just want to finish it real quick. It's very similar to the BCD to binary encoder. So you got 8 lines here, say I0, I1, I2, I3, and then go all the way to I7, and then you get D2, which is your most significant bit, D1, D0, this is your least significant bit. Okay, and looking at the min terms here, for D0, we look at this 1, 3, 5, 7, and then here for D1, we look at this column right here. So we got 2, 3, 6, and 7. And then D2 is basically 4, 5, 6, 7. 4, 5, 6, 7. Okay. Let's move on to our last kind of encoder, which is also very similar to the previous one that we have did. Design a hexadecimal to binary encoder. So for a hexadecimal binary encoder, what would be the configuration? How many outputs we would have? 4, right? So we know hexadecimal goes from 0 to 15, so we have 16 inputs and to the power n, so this has to be 4, right? That's your number of outputs. So again, 0 represents a code of 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. What is the code for E, guys? Correct. 1110 is for E. Okay. And again, you will have these input lines I1, and they go all the way to I15, and these will be your DMSB. It's not really a rule that you have your most significant bit here. You can have your most significant bit here as long as you understand which one is most significant bit. Okay, and then this is your C, B, and A. The significant bit. Okay. Okay, no problem. Okay. I'm pretty sure you can do the min terms here by yourself. So for A, you just look at this column right here and take the ones and then come up. I can just do one for you guys. So A, B, C, D. So this will be 1, 3, 5, 7, 9, 11, 13, and 15. Okay, and similarly you can do it for B and C and D. With this, I'm going to finish today's lecture, and then I'll see you guys tomorrow, okay? Alrighty, thank you for coming, guys.